In SAC 435, problem number 1, you're given some information about a wire segment carrying a current, and you're asked to find the magnetic field due to the current in that wire segment. This is a Biot-Savart problem. We'll get started by drawing a picture of the configuration. So put a coordinate system, call that the x direction, the y direction, and then we need a current. Exactly how this is set up is not specified, just given that we have a current I in this direction where the length of this wire is L. And we're supposed to find the magnetic field due to that current at a point over here, distance L up from the x-axis and L over from the y-axis at that point right there. Now the idea is that each little segment of the wire, say this one for instance, each DL, which I'll consider to be in this direction, the same direction as the current, makes a contribution to the magnetic field at this point. You might consider it point P, which depends on how far away point P is and in what direction. Particular for this configuration, for these points, the direction will all be the same. The contribution to the direction of the magnetic field. So the main thing that we're concerned with is the distance. Biot-Savart can be written as dB, infinitesimal bit contribution to the magnetic field at point P, is equal to mu0, the magnetic permittivity of free space over 4 pi, times the current, times dl cross r, all over r cubed, where r is the vector representing the position of point P, where you're trying to calculate the magnetic field, with respect to the infinitesimal segment of wire of length dl, a segment of wire which itself carries a current I. We can consider the direction of all the contributions. And for any dl, we're going to get a contribution to the magnetic field at point P, which is directed out of the page. Got a circled dot there, and it's best to put that in black. Circled dot is going to be the B, the final B, because every dB is in that direction. We can look at that two ways using the right-hand rule for something curly, something straight. If you point the thumb of your right hand in the direction of the current, the fingers will curl around clockwise as viewed from above, as viewed from a point up there along the positive y-axis. Looking down on this situation, it'll look like a loop that runs, or the magnetic field will form loops that run clockwise about this y-axis. So they would be into the page over there to the left and come out of the page, or in our case the screen at this point. So that would be the direction of it. The other way to look at it is from this right hand rule. No matter where I pick it along there, we're going to get a similar result. The direction is going to be in the direction of dl cross r. dl is down that way. use the right-hand rule for the cross product of two vectors, point the fingers in the direction of that first vector, the dl, and then arrange the hands so that if you close the fingers, and you'll have to close them quite far, but if you close the fingers, they tend to point in the direction of R, and you find yourself with your thumb sticking out of the page, sticking out of the board, right at you in the same direction. And it doesn't matter which piece of the wire you pick. So all the contributions are in the same direction, which makes it much easier to add the contributions. We don't have to do this a component at a time. We get the whole component. This would be the Z component. Out of the board, the magnetic field is going to be in the Z direction in that, if I look at the unit vector I hat in the X direction, J hat in the Y direction, if you cross those, they've got to be in the Z direction. They give you K, which is in the Z direction, and I cross K. Using the right-hand rule, you point your fingers to the right hand in the positive X direction and arrange it. You'll have your palm facing upwards so that when you close the fingers, they point in the direction of the Y-axis and the direction of the J vector, and the thumb will be pointing out of the board at you, telling you that the K direction is out of the board, meaning the positive Z-axis is out of the screen or out of the page if you're copying this down at you, and that's the direction up there. We've established the direction, and also if you recognize what we mean by the cross product, it's a measure of the perpendicularity of two vectors. I think we'll keep on going with the black here. This will be dl in this direction times the component of r, which is perpendicular to dl. And if I break this r up into components, one in the same direction as L, or parallel or anti-parallel to L, and one perpendicular, we see that the perpendicular component is just that capital L, which represented the distance that point P is from the y-axis. I think I'll call this the dl, I'll call it dy. I'll let y be my variable because I'm moving along the y-axis. And I'm going to integrate in the end from y is equal to L down to y is equal to 0. So I'm going to say dl is equal to dy. And I want you to know that since my integral is going to be in the same direction as the current, so I'll be starting out with big values and go into small values. Each change in y, let's consider a finite change in y. Say I go from 29 millimeters down to 28 millimeters. That change in y is actually minus 1 millimeter, the change in the y value. When I go infinitesimal, I get the same algebraic sign. In other words, dy is always going to be a negative infinitesimal value, and it's important to keep that in mind. So we'll get, if I want dB just in magnitude, considering the outward direction, the positive z direction, to be the plus direction, the same direction that we've indicated over here, I'm going to call the positive direction. I have dy times L, dl cross R is going to give something that has magnitude dy times dl. And there will be a minus sign here if I want this to represent the contribution to dB in the positive z direction. If it wasn't, the negative nature of dy would make dB turn out to be negative, meaning that it would be pointing in the negative z direction, and it's not. So we've got that negative sign in there to take that into account. And the r squared, r cubed, let's take a look at this r. R itself is going to be, I'll look at it as a part of a right triangle, where this distance is L, because we are L over, P is L over, and so I want to take the square of this side and the square of that side. That'll be, I'm going to call it plus L squared. That takes care of the base here. Now this piece, let's say all the way up is L, and then up to the point that is currently under consideration, which is an arbitrary point, but we'll consider it to be specified by a value of y. That is to say, it's designated by an unspecified value of y, where y could be anything from 0 up to L, so any piece here of this wire segment. And if it's y up there, an unspecified value of y up there, then the length of this piece is going to be L, which would be all the way up, minus this length, minus y. So R is going to be L minus y, all squared, plus L squared. That's the same thing as that entire expression inside the radical, or under the radical, raised to the 1/2. Now if I cube that, I get that expression in brackets raised to the 3/2, so I can write dB in this fashion. Now I want to take another look at this cross product. How I got it in magnitude. I'm saying this is going to be dB. I could call it dBz, but it's total. The whole b is going to be in the z direction, so I'll just call it dB. I've stuck that minus sign in there to because I knew it had to come out positive. Is one way of looking at it, but I'd like to take a different approach on this whole DL cross R business to make sure that you should be able to do it either way. What we've looked at so far is essentially a conceptual approach. Let's look at a more mathematical approach. The DL, I just want to look at this piece. I'll circle it. I'll circle it in red there for you. So the numerator there. The DL is dy. You can think of that as pointing in the downward direction. Remember, it is negative, times j. And that's not quite right. Yeah, j. A unit vector in the y direction. This is supposed to be an infinitesimal length in the same direction as the current. dy is negative, and j is in the positive y direction, so that negative thing, scalar multiplying this unit vector, gives us an overall direction in the minus y direction, which is exactly the direction of the current. And then I want to cross that into the r vector. Now the r vector is just a position vector. Here it is right there. I can break it into components and say you got to step this distance L in the x direction, so it's L times I. And then you got to step this distance up in the y direction, which would be L minus y. Again, y represents that unspecified. We don't have a value for it. It's just an algebraic symbol, so it's the unspecified position of the infinitesimal current element or wire element now under consideration. So I go plus L minus y. That's how far up I got to go in the j direction. So there's the DL cross R, and j crossed into I. Point your fingers in the j direction. Arrange the hand. The palm will be facing rightward in this picture, so that if you close the fingers, they point in the I direction, and the thumb will be pointing in the minus k direction, the minus z-axis. We said the z-axis is out of the page at you in this picture. So we'll have for this first piece, dyj crossed into the li. We'll have the dy, the scalars out front, times j crossed into I gives us a minus k. And then j crossed into the second term, j crossed into j is just 0. Remember the cross product, the measure of the perpendicularity? Well, these guys, they're in the same direction. There's no perpendicularity whatsoever. So we could be replacing this dl cross r with the minus dyl k, and here it is, the minus dyl, and then I've left off the direction in this piece, but stated and argued that it's in the positive z direction, the same direction as the k. So we could put a k hat over here and put a vector symbol over there. I choose to just calculate the magnitude of b known to be in the positive z direction. So I'll integrate on both sides over here. I'm just summing up all the infinitesimal contributions to the magnetic field at point P due to the infinite set of infinitesimal segments along this wire. And I'm going to wind up with the total magnetic field. There's no, we don't have to resort to the mathematical tools on that side to do the integral. It's just the definition. The sum of the pieces equals the whole. On this side we do have to do some work. And what do we have? I think I'd like to try for a variable substitution. In that this looks a lot like a formula on your formula sheet. I think the first thing I'll do is factor out the L, factor out that minus sign, and then write down, you look up the integral on a table of integrals, either in the back of your book or on your formula sheet, and see which one you want to make this entire expression look like. So that's what we'll have out front, this constant L and the minus sign coming out front there, and then inside the integral, the part that depends on y. That's still there. And again, I want to cover all the infinitesimal wire segments, each being dl long. The wire runs from L, y is equal to L, down to y is equal to 0. So I'll integrate from L to 0 over y. Y is equal to L to y is equal to 0. Now here's the formula that you can find in the table of integrals. This is one we're going to be wanting to look at. I'll just copy it directly. And ours looks something like that. We do have the sum of things squared raised to the 3/2, where one of the things is a constant and the other thing does involve our variable. But it's not quite just the variable squared, so we need to make a variable substitution. I'm going to call u, I'll define u to be L minus y. And then taking differentials on both sides, du is equal to, L is a constant, so the differential there is 0, minus dy. And furthermore, when y is equal to 0, u, I'll call it of y equals 0, is equal to just L. And I just plug in a 0 there, I have L minus 0. And u for y is equal to L. If I plug in y is equal to L, I get L minus L, which is 0. And I think I'm in a position to write down that whole integral for b again as in terms of the u variable. So I'm making a variable substitution. There's the minus dy. It becomes just du. And then the L minus y down here is the u. So that's u squared plus L squared all to the 3/2. And then the limits of integration, when y was 0, u is L. And I think I've actually switched the limits of integration there. So this is supposed to be L down here. Just copying it from the line above. It's from L to 0. And now, when y is equal to L, u is equal to 0. So that'll be a 0 for the lower limit. And for the upper limit is y is equal to 0, but when y is equal to 0, u is equal to L. So our upper limit, when we integrate that over u, is going to be L. And now this is the exact same form as the one that we have in the formula sheet and in the back of the book. We won't be using the minus sign. I think I'll go ahead and erase it even from the generic expression. And now when I substitute that in there, b is mu 0 Li over 4 pi times the x is the u in our case, and the a is L. There's the a, and the integral for the generic expression, it corresponds to L, or L corresponds to it. So I have L squared times the square root of u squared plus L squared. And I need to evaluate that from 0 to L. So b is going to be mu sub 0. That's a permittivity of free space. Don't confuse that with a u. Actually, one of these L's will cancel out. So I'll go mu 0 I over 4 pi L. And then that L it's a constant, so I can factor that out. And then this expression, the u over the square root, evaluated from 0 to L. So it'll be L over square root of L squared plus L squared minus 0. 0 divided by something is just 0. There will be a non-zero part in the denominator, so it is well defined. And so I can ignore that minus 0 part. The L cancels out over here. This is going to be the square root of 2L squared. I can factor out the 2, call it the square root of 2 times the square root of L squared, or the square root of 2 times L. So I've got mu 0 I over 4 times the square root of 2 times pi times L. as the final answer. To emphasize the vector nature of it, I'll reinstall that information that it's out of the page, which is in the positive z direction, and just say that it's in the k direction, and multiply it by the unit vector in the unit vector k, which is the unit vector in the z direction.